Okay, welcome everyone to the Zoom Algebraic Geometry Seminar. We're very fortunate to have Elana Kalashnikov of the University of Waterloo in Canada today, and her title is Undoing Toric Degenerations, a Grassmannian Analog of Green-Plesser Mirror Symmetry. Elana?
Thank you. Thanks for the introduction. Yeah, so today I want to talk about how you undo toric degeneration, specifically in the context of mirror symmetry for Grassmannians. So let's just go back to the oldest example of mirror symmetries, which is the Green-Plesser mirror symmetry construction. So the most basic, I guess, and famous example is the quintic in P4, which mirrors the quintic inside P4 modulo a finite group G, which I'll talk more about later in a minute. And then more generally, you could take a Calabi-Yau hypersurface inside projective space modulo a finite group, and it's going to mirror another Calabi-Yau hypersurface inside the same projective space modulo a different finite group, which you might call the dual group. So when you start thinking about how this construction was generalized, sort of the different generalizations come from how you view projective space. So projective space is an example of a Fano-toric variety. And so the generalization of this projective example to mirror symmetry for toric varieties, Fano-toric varieties, is due to Badirev and Borisov. And then you could also think of projective space as an example of a weighted projective space. And there the generalization was done by Berglund-Fuchs. And then finally, projective space is, of course, an example of a Grassmannian. And so it's a really natural question to ask, what should this picture look like? Can it be generalized to Grassmannians? And that's what I want to talk about today. And this is going to be joint work. Everything I talk about is joint work with Tom Coates and Charles Durand, who just introduced me. So before I start talking about the Grassmannian, let's just take a closer look at the original construction. So we had that the Calabi-Yau hypersurface in projective space mirrored a Calabi-Yau hypersurface inside projective space modulo a finite group. So now I'm going to call this finite group Hn-1 for the projective space Pn-1. And let me tell you what Hn-1 is. So I'm going to describe it in two steps. So the first group is going to act on C to the n, and then the second group is going to be the action you get when you take the GIT quotient that produces projective space. So the first group is H tilde n1. And this is going to be tuples, n tuples of nth roots of unity. So each zeta I to the n is equal to 1. And the product of the zeta i's is equal to 1. Sorry, I just realized this is n comma 1 that I want to talk about there. Sorry. So my group is Hn1. And so first Hn1 tilde looks like this. And of course, this group here acts on C to the n. And projective space is the GIT quotient of C to the n mod C star. And so you can get an action of Hn1, which is given by taking Hn1 tilde and quotienting by the action, the intersection of the actions of Hn1 tilde and C star on C to the n. So I'll write that down. And this is going to act on P to the n-1. And this here is just the diagonal elements. So all the entries are the same. So that's the finite group that appears under this the original example of mirror symmetry here. So one thing which I want to point out is that this is an SL action. Just meaning that HN1 tilde acts through SL on C to the n. The determinants of the actions are 1. So how can we generalize this to the Grassmannian? So I claim that the following is a very natural generalization. So the Grassmannian can be constructed as a GIT quotient, just like projective space. My Grassmannians are always Grassmannians of quotients. So n is the ambient dimension and r is the dimension of the quotient space. And it's a GIT quotient of R by n matrices by GLR. And so just like in the case of projective space, I'm going to define the generalization of the group in 2 steps. So I'm going to take H tilde and R to be n tuples of nth roots of unity, just like before. And instead of the SL condition, though, is going to change slightly. So instead of just taking that their product of all of the zeta i's is equal to 1, I'm going to say that the rth power of it is equal to 1. So now, note that this group acts on the Grassmannian, on the matrices. So where each zeta I is going to scale the ith column of the matrix. And also, this condition I chose, this condition right here, is really the SL condition you want. So it acts via SL, because if you think of R by n matrices as a big vector space, then this is acting on each row, and so the determinant is going to be the product of all the zeta i's raised to the r, rather than just raised to itself once. So this condition means that this group acts via SL. And now, just like before, the group that acts on projective space is a quotient of this. So I'm going to let HNR be H tilde NR modulo H tilde NR intercept GLR, which again is just going to be the diagonal elements. And so now HNR acts on the Grassmannian. So this is just a very straightforward generalization of the group you get in the projective space example. And so the main result that I want to talk about today is the following statement. So, which is vague, but I'm going to go into detail. So the result is that if you take a Calabi-Yau hypersurface inside the Grassmannian, and then another Calabi-Yau hypersurface inside the Grassmannian modulo this finite group, these two Calabi-Yau varieties are related via mirror symmetry. So this related here is doing a lot of work. So as suits the Grassmannian, the story is quite a bit more complicated than in the projective space case. And so the story I'm going to tell you today is going to involve some of these ingredients here. So it's going to involve a variation on polytope duality. So on the polytope duality, that is the basis of Batty-Borisov mirror symmetry. It's going to involve toric degenerations. It's going to involve some toric variation of GIT and some toric blowups. And then it's also going to involve toric undegenerations, meaning I'm also going to take what I think is the result of the toric degeneration and tell you how you can undegenerate it into something. So I hope, so this is going to be a rough outline of my talk, actually. So it'll take me about till the end of my talk to really explain what this main result is saying precisely, how these two Calabi-Yau varieties are related via mirror symmetry. And I'll talk about each of these ingredients in the order that are here. So before I do that, let me just give some context. So just to make sure we're on the same page here. So very, very roughly, what does mirror symmetry for Calabi-Yau varieties look like? Well, you have one Calabi-Yau variety, which isn't, let's say it's n-dimensional, and it's supposed to mirror another Calabi-Yau variety, which is also n-dimensional. And one thing that you would expect is that you get a mirroring of Hodge diamonds. On the other hand, mirror symmetry for Fano varieties looks a bit different. So if X is an n-dimensional Fano variety, you don't expect its mirror to be another Fano variety. Rather, it's the Landau-Ginzburg model, or more specifically, in some conjectures, a Laurent polynomial. So this is going to be a Laurent polynomial in n variables. And then there's a number of senses in which you could say a Fano variety is mirror to a Laurent polynomial F. So one way you might say it is that the quantum period of X, which is something which is made out of genus Theorem of Witten invariants, is equal to another period coming from the Laurent polynomial called the classical period. So if you have an equality of periods, you'd say these two are mirror. But in a more enhanced version, or in addition to this, you might require another thing, which is that if you take an anti-canonical Calabi-Yau inside X, then you would expect that its mirror, or a mirror, is obtained by choosing a compactification of the fibers of the Laurent polynomial. So that also gives you a sense into how mirror symmetry for Fano varieties and mirror symmetry for Calabi-Yau varieties are expected to be related. So this very rough picture is pretty well understood for toric varieties. So, but let me tell you a bit about what's known for Grassmannians. So for Grassmannians, which I guess are probably the best understood of non-abelian GIQ quotients. So one of the first proposals was due to Badirev, Chok, and Fontaine, Kim, and Van Straten. And so they proposed the following. So if you take your anti-canonical Calabi-Yau inside your Grassmannian, Gur, and R, they said, well, you can take a toric degeneration to Z prime. So toric degeneration of the Grassmannian to some toric variety, which I'll call XP, and then Z degenerates to an anti-canonical Calabi-Yau inside the Fano toric variety. And now, since it's a toric variety, you can apply Badirev-Borisov mirror symmetry and get Z prime check inside XP check. So that's roughly speaking their proposal. And there, in many important senses, this proposal is correct. So this here, specifically, the toric degeneration they propose, this is the Gelfand-Settlin toric degeneration. And it's, if you take the Laurent polynomial mirror of this toric variety, so if the Laurent polynomial mirror of XP is the mirror proposed by Iguchi-Horixiong. So this is the Iguchi-Horixiong mirror. And a theorem due to Marsh and Reach is that this EHX mirror has the correct period. So what I'm saying is that this proposal here, at least for the ambient Fano variety, really does give you a Laurent polynomial mirror in the sense of this picture above. But it's sort of unsatisfying, especially for the Calabi-Yau, because we've taken a toric degeneration to get into the toric variety world, but how do you leave it? And that's what I want to talk about today. So some applications of the main result I'm going to explain to you are going to be, we're going to see Grassmannians on the mirror side. So it's going to give you an answer to this question. It is going to give a compactification of the EHX mirror. So that's going to be a candidate mirror to the anti-canonical Calabi-Yau and the Grassmannian. And then also, if we go back to looking at this toric degeneration here, it's a really beautiful and influential toric degeneration whose combinatorics have come up in a lot of different places. And so we're going to see some new combinatorial constructions coming up on the mirror side from these ladder diagrams. All right. So are there any questions? Otherwise, I will start talking about the different ingredients in the story. Okay. I haven't heard anything. So let me tell you first about the variation on polytope duality that we're going to need. So let's let P inside a lattice NR, so it's a lattice polytope, be a reflexive polytope, and I'm going to let M be my dual lattice. And so I want to define the primitive dual of P as opposed to just the regular dual of P as follows. So the primitive dual of P is a polytope Q, which is formed by taking the preimage of the usual dual of P under a map. And this map here is an inclusion of lattices. Where the sublattice M bar is the lattice spanned by the vertices of P dual. So basically, to produce the primitive dual, you take the usual dual of a reflexive polytope, and then instead of viewing it in the lattice dual to N, you view it inside a sublattice spanned by the vertices of the dual polytope. So let me say a few remarks about this duality. So first of all, primitive duality is a duality exactly if the vertices of P span N. Otherwise, you're not, if you apply it twice, you're not going to get back what you started with. And then secondly, the polytope for projective space is self-dual under this, this primitive duality. And this gives an explanation for why in the green Plessy constructions, you see projective space on both sides of the mirror, granted with a finite group on the other side. So let me explain that a bit further. So how does mirror symmetry and primitive duality relate? So let's fix P and Q, where Q is the primitive dual of P. So then Body-Rev-Borisov duality takes XP to XQ modulo a finite group G, and it takes XQ to XP modulo the same finite group G. So this here is Body-Rev-Borisov, and this group G is isomorphic to the lattice quotient m mod m bar, using the notation in the definition, which you could also describe as m bar dual modulo n. So these lattices are going to act on xq and xp so that you can form this quotient. So that's what mirror symmetry does here. And then you can be a little bit more general. So if you take, say you have m bar, which is the lattice spanned by the vertices of q, sitting inside M, and you take an intermediate lattice M prime, and then you dualize this whole sequence to N sitting inside N prime, sitting inside N bar, then Bati-Rev-Borisov duality does the following. So it takes XP modulo the group N prime mod N to Q modulo M prime mod M bar. And so this gives, this is what gives you the series of examples in the green cluster paper that I started the talk by discussing. So choosing different intermediate dualities is going to give you different mirror pairs here. So that's the duality, the variation on polytope duality that we're going to need. And now I want to tell you about the Gelfand-Zetland-Tarski generation. So I'm going to need to describe it to you quite explicitly. So I'm going to introduce some of the combinatorics of it. So to describe, so a useful way of describing the Gelfand-Zetland-Tarski generation is via ladder diagrams. So the ladder diagram for the Grassmannian GUR-NR is just an R by n minus R dimensional grid. So for example, for GUR-42, it's a 2 by 2 grid. For GUR-73, it's going to be a 3 by 4 dimensional grid. And then the next thing you want to do is you want to make it into a quiver. So to make this grid into a quiver, you have to add vertices and an orientation. So you add vertices by adding all the interior vertices. So just one here or 6 in this example, and then also always add the bottom left and the top right one. And these external vertices are useful to have labels for them, so I'm going to label them 0 and 1. And then the orientation is that you can move along the grid up and to the right. And so then with that ingredient, with those ingredients, you can define the ladder quiver. So I'm going to denote the ladder quiver L, Q, and R. And it's obtained by looking at, so you take the same vertices that you had over here, and then arrows are given by looking at paths between the vertices which don't pass through any other vertices. So for example, if we look at this example here, between 0 and this middle vertex, there's 2 paths following the orientation, and they correspond to these 2 arrows. And then also there's 2 paths from 0 to 1, which don't pass through any vertex, which give you these. So that's how you produce a quiver. And then Gans, Celia, and Lakshmibai, as well as so they proved that this is a Tarski generation, and then Bati-Revchuk and Fontaine, Kim and von Straten showed that this ladder quiver describes that Tarski generation, give this theorem, which says that, so there is a Tarski generation from the Grassmannian to the moduli space of representations of the ladder quiver. So this here is the moduli space of representations of L, Q, and R with dimension vector L1. And this is a toric variety, as it should be, because it's a Tarski generation. And it's a phanotoric variety, so it comes from a polytope. So I'm going to call the polytope PNR. So this is the toric variety XPNR, where you get your toric variety by taking the spanning fan of that polytope. So I'm going to let as I said, I'm going to let PNR be the associated polytope of this toric variety, and I'm going to let QNR denote its primitive dual. So I want to tell you a bit more about these polytopes and how you can describe them using the lattice quiver. So I'll go through each of these boxes more carefully, but I'll just tell you what the indexing sets are in each case. So if we look at PNR, the vertices of this polytope are going to be indexed by arrows in the ladder quiver. And the weights of the toric variety are going to be indexed by vertices of the ladder quiver. Paths are going to be, QNR, the vertices of that polytope, the primitive dual polytope, are given by paths from 0 to 1 in the ladder quiver, so between those two external vertices. And the weights of the toric variety are going to be given by something I'll call coverings of the ladder. So let me explain what I mean more carefully. So firstly, vertices of PNR are, first I'm going to tell you about the weights. So the weights, because that is a bit easier. So the weights of XPNR are just given by taking the adjacency matrix of the ladder quiver. So that's going to give you a matrix, and the columns are going to be indexed by the vertices of the ladder quiver, which is why I said the weights are indexed by the vertices. Alternatively, you could describe the toric variety using a polytope. And so you're going to get a vertex of the polytope for each arrow inside your ladder quiver. So to describe how you do that explicitly, it's a bit easier to use the dual quiver of the ladder quiver. So the dual quiver is this quiver I've drawn in purple. So you add a box to each internal vertex and then arrows. And so the important feature of this is that arrows in your ladder quiver are in one-to-one correspondence with arrows in the dual quiver. So vertices of the polytope are indexed by arrows in your ladder quiver, but I can just tell you how they're indexed by arrows in the dual quiver because there's a one-to-one correspondence between these two sets. So how do you get a vertex if you're given an arrow? So let me tell you how to do that. So let's let n be a lattice with a basis BA, where A runs over the highlighted arrows. Which I'll call the basis arrows. So in this example, I've highlighted some of these arrows, basically one for every vertex, and I'm going to label the corresponding basis element to the lattice VA. So then the vertex VA of PNR that you get for any arrow in the dual quiver is just obtained by writing any particular arrow inside the basis as a sum of basis arrows. So for example, this green arrow here I've highlighted is an arrow in your quiver. And you'll note that you can get this arrow here from this vertex to here just by using arrows in the basis by taking the path like this. Although you do have to go backwards along these two arrows here. And so that means your vector, your vertex, is the sum BA1, so that's this one here, plus BA2, plus BA3, plus BA4, minus BA5, minus BA6. And the negative signs correspond to the fact that you're going backwards along those arrows. So if you go through all the arrows in the dual quiver, then you just get all of the vertices of P and R. So now you know how to write down P and R. And the next thing I want to tell you about is the primitive dual of P and R. So the vertices of Q and R are going to be indexed by partitions or by paths from 0 to 1 inside the ladder quiver. So these are the same things. So I'm going to look at partitions, lambda, which fit inside an R by n, an R times n minus R dimensional box, meaning that if you take the partition 2, 1, then it sits inside a 2 by 2 box. It would also fit inside a 2 by 3 box, but it does not fit inside a 2 by 1 box. So that's just what I mean by fitting inside a rectangle. And so it's easy to see that paths in the ladder quiver between the external vertices exactly correspond to these partitions just by looking at what they cut out, what shape they cut out. So for example, in this example, so if you take this particular path from 0 to 1, that's I've highlighted in green, you just look at the partition that's described above it. And that is, of course, going to be a partition that fits in the right size box. So in this particular case, the partition would be 4, 2. So I'm going to talk about paths between 0 and 1 and partitions completely interchangeably because they're the same things. So that's how you go from partitions to paths. What I want to tell you about are how you get vertices. So it's like this. So I'm going to let M be the lattice dual to N, and I'm going to let BA check be the basis dual to the BAs. And then I'm going to set M lambda, so for any particular lambda, to be the sum over arrows where you add that arrow if lambda crosses that arrow. So for example, here, this path here, you have to look at where it crosses a basis arrow. So that's going to be right here and right here. And so you'd have 2 summons in that example. And so then you get Q and R like this. So Q and R has vertices B lambda obtained by scaling M lambda by a factor of n and then shifting. And you view these as vertices or as vectors inside the lattice spanned by n times the basis and then the element you shift by. So that tells you what Q and R is. And then I also want to tell you what the weights are because that will give you another perspective on this type variety. So these can be indexed redundantly by coverings of the ladder quiver. So what do I mean by a covering? So I'm going to call a K covering of the ladder quiver to be a choice of partitions, lambda 1 to lambda s, let's say, that all fit inside an R by n minus R dimensional box, such that their union, when you view them as paths, precisely covers the ladder quiver K times. So an example will probably make things clearer. So if we take GER42 and we look at this set of partitions here, so box 2, 1, 2, 2, and the empty set, then how does this cover the ladder diagram? Let me draw the ladder quiver for you. So it looks like this in this case. And you can see that if we write down the paths of each of these on this picture, we're going to cover it exactly once. So if we take this box one, it gives you this path here. If you take 2, 1, and it gives you this one here. If you take 2, 2, it's going to give you the last one. And then finally, the empty set is going to give you this here. Oh no, I use the same color twice. Oh, you'll forgive me. So altogether, we've covered this quiver exactly every single path. And this quiver is covered exactly once. So this is a 1 covering. And so that tells you a redundant form of the weight matrix, which tells you how to write down the toric variety as a GIT quotient. So the weight matrix has columns indexed by partitions, and it has rows indexed by covering diagrams, and the entry at a particular covering diagram and a particular partition is just the number of times that lambda appears in that particular covering diagram. So now we've gone over how you obtain XPN, how you write down the polytopes of PNR and its primitive dual. So PNR was the Gelfand-Sutherland toric degeneration, and we've also talked about the weights. And now we can use the combinatorics to say something about the geometry. So to say, and this is where we're going to see the blowups and the variation of GIT that I mentioned at the beginning of my talk. So we need one more definition before I can tell you what's going on. So if a lambda is a partition fitting inside the usual box, then I'm going to call it an arrow partition for the Grassmannian if it looks like, if it's of the following form. So there's 2 possibilities. So possibility 1 is it looks like a rectangle that's as wide as possible. So that means it's n minus r wide, and let's say a tall, together with another partial row. So that's one type of partition. That would be an arrow partition. And here A is going to range between 0 and r minus 2. Alternatively, it could look like the transpose of this. So a maximally tall rectangle. So it's going to be r tall, and let's say b wide, together with a partial column now. And here B ranges between 1 and r minus 1. So the arrow partitions form a special subclasses of all of the partitions fitting inside the right dimensional box. And so because we know that that vertices of Q and R are indexed by partitions, it's telling you what it's telling you a special subset of the vertices of that polytope. And so the theorem, which is why they are special, says the following. So let's let Q and R bar be the convex hull of the lambda when lambda is an arrow partition. So you look at all of Q and R and you just forget all of the vertices which aren't indexed by arrow partitions, and you look at what you have left, and what you get left is exactly isomorphic to the Gelfand-Sutherland polytope. So this tells you something about how the toric varieties associated to each of these polytopes are related, which I'm going to describe in a picture. So the picture is part of a corollary, which says that there exists a toric variety Y fitting into the following diagram. And now I will draw that diagram for you. So we have, what are all the ingredients we have so far? So we've got XPNR, and we've got XQNR, which is its primitive dual. And then this corollary says that there's a toric variety Y, which is in fact weak Fano, such that it's a blow up of XPNR. And it's a toric variation of GIT of XQNR. And this here is a K equivalence. So this follows pretty immediately from this theorem telling you how QNR bar and PNR are isomorphic, because, okay, let's start here. If you want to get to QNR, I said you need to add a bunch of new vertices. How do you add vertices to a polytope in using toric geometry? You just blow up at those new rays. So that's going to give you something Y, but the fan structure is going to be different. And so to go between the two different fan structures, you need to vary the stability condition. But you're not changing too much, because you know that even as you vary the stability condition, the polytope given by the convex hull of the rays is going to stay the same when you do that. And that's what it means to be a K equivalence in this context. So you can think of this as being a sort of geometric transition between these two toric varieties. I'm putting it in quotation marks because it's a lot more general than the usual definition of geometric transition. But it is very similar. And so let me tell you now what the mirror picture is going to look like. So because of how primitive duality behaves under Batty-Rove-Borisov mirror symmetry, we just get the whole picture in reverse. So we get XQNR modulo some finite group mirroring XPNR. We get XQNR mirroring XPNR modulo a finite group G, and then Y mod G fits inside the same picture where you would have the same types of maps as before. And once again, you have this version of a geometric transition. And so one thing which I think is worth noticing about this picture is that the expectation for geometric transitions under mirror symmetry is that, you know, if XPNR and X2NR are related by a geometric transition, then their mirrors are also related by a geometric transition in such a way that the rules of the maps are reversed exactly like we see here in this picture. So that's that corollary. And let me just add the one more piece of information which is that we know that there is a toric degeneration of GUR and R to here. And so we have this much more detailed picture now of what happens under mirror symmetry when you look at this, the result of this toric degeneration. And now I want to start talking about how do you undegenerate on this side here. So which, if any, or all of these toric varieties are the special fibers of a toric degeneration is something nice. And I'm going to start by talking about this guy right here. So one important piece of information, which I forgot to say, is that this finite group G is isomorphic to Z mod NZ to the dimension of the Grassmannian GUR and R -1. So now I'm going to talk about how you unwind the toric degeneration here. So let's go back to how you describe XPNR, because that's going to be important to unwinding the toric degeneration. So I told you what the weight matrix was, which means that you can tell, I told you how to write this down as a GIT quotient. So there should be 2 lines there. So it's, as always for a toric variety, the GIT quotient of a vector space where the basis is indexed by arrows of the ladder quiver. Modulo a torus of dimension equal to the number of vertices of the ladder quiver. We're going to need to understand this group action. And so just like in the case of HNR, we describe it in 2 steps. So G tilde is going to be tuples of nth roots of unity. Put that in. Where you get 1 for every arrow in the ladder quiver, such that it satisfies an SL condition. And then the group G is just going to be G tilde modulo a subgroup where you take the intersection of the G tilde action on this space here and the action of this particular torus here as well. And that's going to act on the toric variety. So that's what XPNR mod G is. And to understand it, we need to understand how XPNR was obtained as a toric degeneration itself. So let me remind you or tell you how to do that. So it's to see it as a special fiber of a toric degeneration, you see it as a subvariety inside projective space, where it's projective space of dimension n choose r-1. So I'm going to so this is indexed by Fluker coordinates. So I'm going to let p lambda, where lambda is a partition, be the coordinates on this projective space. So you may normally think of Fluker coordinates as being indexed by subsets of 1 to n, but this is really the same thing. So if you have a partition sitting inside an r by n minus r dimensional box, then it corresponds to a size r subset of 1 to n. So one way to obtain it is by to attain this set here is you just label the ladder quiver like this, following this obvious pattern, and then you draw the path that the partition corresponds to, and you look at what labels you went by. So for example, this partition here, 2 passes the labels 1, 2, and 5, and that's going to give you the subset of 1 to 7 that indexes that particular Fluker coordinate. So we see 2 partitions are incomparable if neither one sits above the other. So for example, if you take this partition here, and this partition here, you can see that they cross and neither one is above the other. And so this is an example of an incomparable partition. Whenever you're given an incomparable pair, you can define sort of a maximal one and a minimal partition, where you just take the one which follows the top path and the one which follows the bottom path. So these are going to be leading terms of your Fluker relations. So Fluker relations look like 0 is equal to p sigma times p lambda, where sigma and lambda are an incomparable pair. And then the next term is going to be the binomial corresponding to their max and min. And then you have a bunch of other terms as well. And so if you take all of these Fluker relations, you cut out GER and R inside this projective space. And then if you scale all of these other terms to 0, so you just have the degenerate Fluker relations left. These guys, where you just have the first 2 terms. Then this cuts out X, P, and R. And so that's how you see it as a degeneration. It's a Sagi basis degeneration, but so you just add parameters corresponding to these extra monomials, and if you scale them to 0, you get this here, and that's the family which has XPNR, that special fiber. So remember, we have this group action G acting on XPNR, and we can use the fact that it sits inside projective space to extend the action of G to PNR minus 1. So Z to A inside the ladder quiver acts on P lambda with weight, just taken by taking the product of the Z to A's over all of the arrows inside that partition. So partitions correspond to paths, and so you can see whether an arrow lies inside that path or not, and if it does, it multiplies on P lambda. So we've extended the action of XPNR to PNR minus 1, and as a sanity check, we should check that the degenerate Pluker relations really are G homogeneous, which of course they are. So if we look at, say, this incomparable pair here, and then we look at the next term in the equation that gives you the degenerate Pluker relations, well, G acts on this just by taking a multiple over all the Z to A's, where A is in the union of these two paths, but the union of these two paths are exactly the same as the union of these two paths, so it acts on each term with the same weight. So it is, these equations are all homogeneous. On the other hand, G definitely does not preserve the Grassmannian. So if you add back in the extra monomials that you've forgotten, G no longer preserves those equations. And so now we need to think back to the group that I started my talk with. So remember, I defined HNR as the group which naturally generalized the green Plesser group that appeared in the mirror of the quintic. So it was indexed by tuples of n tuples of nth groups of unity, quotient by the diagonal one. And you can view it as a subgroup of G by just taking a natural embedding in it. It turns out the embedding comes from the same labeling that you use to identify partitions and Pluker coordinates. So Z to I equals 1 to n just maps to to Z to A. So like these are indexed by arrows in the ladder quiver. And at the Ath arrow, you just take the product of Z to I's, where you take the product over over labels of that particular arrow. So that tells you how to map from one to the other. And then a somewhat surprising theorem is that HNR is exactly the maximal subgroup of G for which GURNR is an equivariant subvariety. So, we start with XPNR, we have a group G on it. This is coming heavily from toric geometry. G is quite complicated in its action on XPNR. But if you just look at what is the maximal subgroup of G for which the Grassmannian is the equivariant subvariety, HNR just falls out of the sky. And so this is the first step towards showing the main result that I talked about at the beginning. So to get there, I want to just take the toric degeneration that we've been looking at and just construct it as an equivariant family, a G equivariant family. So I'm going to let Z be the family cut out by Pluker relations with extra parameters. And I'm going to let C to the K just define the extra parameters that I need, so that if I take Z and I intersect it with the fiber where all the parameters are set equal to 0, I get XPNR. And if I intersect it with they're all equal to 1, I just get the Grassmannian. So that's just the family that we've been talking about. And now we can extend the action of G to CK so that this Z is G equivariant. So we just define the action of G to be whatever is necessary to do this. So now we have our toric degeneration being G equivariant, so we can take the quotient. And the theorem, which is the main result, is that the family, the quotient family, so you take the family you started with and you quotient by G and you quotient the base by G as well, has special fiber XPNR mod G and general fiber GNR mod HNR. So this really is, XPNR mod G really is a toric degeneration of the natural generalization of the green Poisson mirror. So finally, what we get is that we have this picture again, which I talked about, where we have everything we talked about before, and now we can add that there's a toric degeneration of GNR mod HNR to XPNR mod G. So to summarize, if you take the Grassmannian or the anticanonical Calabi-Yau Grassmannian, you take a toric degeneration, and then you take a geometric transition, you apply mirror symmetry, and you undegenerate, you get GNR mod HNR. So that's how these two are related via mirror symmetry, or you could do it the other way. You could take a toric degeneration, apply mirror symmetry, and then do a geometric transition and get the relation as well. So once you have this piece here, well, you know, you can use this to undegenerate Y mod G as well. So basically what you get is you got a blow up of the Grassmannian along a bunch of somewhat complicated linear subspaces modulo HNR. And now we can start talking about a compactification of the Gucci-Horry-Schunck mirror. So remember the Gucci-Horry-Schunck mirror was a Laurent polynomial mirror for the Grassmannian, which came about by constructing it as the mirror of XPNR. And so it naturally compactifies to a family of Calabi-Yaus inside this toric variety here, but because it's this VGIT is crepant, it also gives you a family right here, and hence something inside the blow-up of the Grassmannian. So that's the last theorem I want to say, and that's the key steps of the proof, which is that the family of hypersurfaces, some P lambda to the n over lambda, an arrow partition plus psi, that's my parameter, times the product of P lambdas, where lambda is a maximal rectangular partition. So if you look at this family of hypersurfaces inside the blow-up, particular blow-up of the Grassmannian modulo HNR, this is a Calabi-Yau compactification of the HX mirror. And so in particular, based on expectations of mirror symmetry for Fano varieties, this seems like a reasonable possibility for what the mirror of the Calabi-Yau hypersurface inside the Grassmannian. So I think I'll stop there. Thank you very much for listening to me.
Thank you, Elana.